So, good morning and this is the first lecture, first Monday of this semester. So, today is the first day for all the courses, whoever is getting in this slot, So, this course is CE617, as you know, elastic plates and shells, and so I will tell you about what are plates and shells. Before that, I will also give you some simile, what is the relationship of plates and shells with something which you already know, which you have already done. So, that I will tell you. Some of you are new, so you may not be knowing my name, I do not know, I mean, or you saw it from the registration website. So, I am Tarun Kant, and I joined in January 1971 this department. So, it is almost 44 years complete. 45th is will start very soon after few days. So, and but if you take my my entire how long I have been here in Mumbai. So, it has been very long, because I came here in 1963 as an undergraduate student, okay, and joined hostel 5. And so, it is almost 51 and a half years. There was nothing, no road, no shopping, no bus. From here we had to come in those days to Vikhroli station, and IIT used to run 4 or 5 times during the day their own buses to bring some people, whoever. So, our entry point was Vikhroli station. You just wait there till the next bus comes after 2 hours, and then you will be brought back to near chemical engineering. Though that was the time. So, Mumbai city was much better in those days. It is has become very crowded, very dirty, very environmentally unsafe. But then in those days things were much better. Life was comfortable. You could travel in local trains without much difficulty. Ladies were safe in those days. We could see ladies traveling, in trains even after midnight. Sometimes used to come from city after seeing a movie, in metro or some place. So, yes, trains used to be. And once I have also walked from Vikhroli to IIT, because there was nothing in the night. So, it is about 4 kilometers. It takes 1 hour. So, this is how. So, okay. So, elastic plates and shells, this is the course, and some of you have taken my first course, that is advanced solid mechanics, which is also called theory of elasticity. Theory of elasticity also is a very classic subject, and since I am a classic person, so this course also is classic. Theory of elasticity has more than 200 years of history, and this also has about more than 160 years of history, 100 and around mid 19th century, 1850 onwards, work started on plates and shells. So, this is the history. So, but we have to learn, because these structural forms, they are present in nature in large numbers, and we have to analyze. You have to know the state of stress. Ultimately, if you know the state of stress in any body, you can design it better. If you do not know, you will have to use some approximate method. So, here, so you have a theory which will give you some methods, it will provide you some basis for finding out the internal state of stress. So, that is our job. So, this is how it goes. Now, what I will give you, because so that there is no confusion, this course is in slot number 3, you all know. So, I need 1 hour extra. Please tell me when we can have that. Even it can be in continuation, 2 hours at a stretch. Today also it can be 11:30. If you are free at 11:30, yes, we can have. Okay. So, that you tell me. Is it okay? 11:30 on Monday? 11:30, 12:30? Okay, we will have a break of 5 minutes in between, and then. So, thank you. So, this is because I am slow. You see, basically I have found that I am bit slow. I take more time in delivery, and I cannot cover what I want to cover in the entire course. So, that is why and it is 6 credit. You know the meaning of 6 credits? 6 credit, what is the meaning? Okay, Srinath. For that course, twice. 2 for every lecture hour, 2 hours you have to put in on your own. Own means everything included, on your own study, assignments, submission, whatever, but 2 hours. So, that if you have 5 courses in a semester, so you have 5 into 6, 30 hours of your own work, and 5 courses into 3, 15. So, total it is 30 plus 15, it is coming to only 45 hours, not much. In Soviet Union, their standard is 60 hours. They work for 60 hours every student. Europe, it is all 60 hours. Britain, it may be 30 hours, because they do not teach anything. They want you to learn through your own. So, this is, and attendance, as far as I am concerned, so I take it compulsory. No, there is no freedom. You cannot take it, I can do it from home. No, please. So, if you have registered for this course, it is compulsory, and unless there are some eventualities, if you are sick or there is some urgency, you please tell me. Now, we have mid semester. So, I have just written here about 40%, end semester again about 40%. Assignments, homework I give something at least about 10, minimum 10 assignments I will give, which will require, there are 15 weeks. So, each assignment will will require some study plus submission. So, I have put here 10%. Attendance and my own impression, I will put, finally, I will see somebody whether he can be between A or B, depending upon how sincere he was, what kind of his face was. So, that will also matter. So, this is how it will be. I hope you have no problem with this kind of assessment. Then next thing which I forget mostly, but then last night I spent some time. Okay, we must have textbooks, because without book you cannot, because lecture is one part, but you must have some textbooks. So, one the most classic textbook is by Timoshenko and Wynwaski Krieger, and Theory of Plates and Shells. Second edition came out in 1959, but first edition was maybe around 1937 or 40. Plus, he had also, Timoshenko was actually from Soviet Union. He, after war, he ran away from there, he left the country, he came to Turkey. So, he was a professor in Turkey. Turkey is very good in mechanics, Turkey. They are very good people, and they have a tradition of, same thing is Soviet Union, they are very good in mechanics. So, then he came to Turkey, and from there he came to United States. Which university? Which university he served? It will be there in the book, if you read the book. Stanford. No, Stanford. Most likely I think Stanford, yes. Stanford, that is what my mind is. No, it is Stanford, yes. He spent his time in Stanford throughout. And and he has given Timoshenko, the first author. Of course, he always, most of his books, he has somebody or the other as co-author. So, normally you have to depend on your students or some colleague. So, that is how he has, but then he gave the leadership. He is the first person who gave us textbooks on mechanics subject, on every aspect of mechanics, solid mechanics especially, in English literature. Before him there was nothing, no textbook. Of course, there was something in French. French are ahead of English, So, British also had no book. So, it was only Timoshenko who is responsible for giving, because once you have a textbook, then it can be taught. Many teachers can start, it becomes easier for teachers to start a course. Otherwise, you have to refer to journals. Then the other I thought that this is okay. Other one is see, Jane Reddy. You know him already. He is a very famous person. He will be 70 now, 70 years. Yes, in the month of August. I met him only last week. He was here in Kharagpur. I met him in IIT Kharagpur last week. So, he has written a book, Theory and Analysis of Elastic Plates, and that is in 1909. Then this is about plates. Of course, the first book is also plates and shells. This course is a combined course. Earlier we used to have two separate courses, but because since semester number of courses became too many, so we have combined some courses. So, we have combined now plates and shells into one. So, I will have to do go faster and then try to cover as much as, it is not covering, you see, it is uncovering, I do not have to cover too much, but even if I cover basic things, I think it should be, and if you get the confidence to read on your own, it is, I have served the purpose. So, teaching is not that you cover the syllabus. We do not have syllabus in IIT, not this much, this topic has to be covered, this topic has to be covered, it is not necessary. So, but still we try to cover the basic fundamental, whatever is required. Then another course, another book that came, and see, Timoshenko book is not very, in the modern times I will not say it is very well written book. It has lot of material, and hard work has gone into it, in compiling, but then as a textbook it becomes difficult. So, on shells, the first book I will say on the theory of shells, the first book, that is, you can say, yes, it was very significant addition to our mechanics, was by Krauss in 1967. That is the year when I had graduated. So, this book came, Thin Elastic Shells. Then we have our own person, Professor K. Chandrasekhara. He retired about 10 years ago. So, I do not know where does he stay now, but he worked in IIC Bangalore. He has written books on both plates and shells both. I do not have the reference of shells here, but it is a thing you can find out from the website and tell me the reference of his, which book, which publisher, his shells book. And he also worked in this area. So, those people who have worked in this, certainly they have more, the book will be more valuable. So, this is the textbook, I will say. I have not listed too many. I think you can get all these books, and then, but then this will not be enough. There will also be some reference books. Reference books means once in a while you will have to refer, and most important reference book will be on shells, that is thin shell theory. See, you please note this word thin, why they have added thin. Some titles are having thin, not all, but some. Thin shell theory, Novozilov is from Soviet Union, very good book, very good compilation, and there is a lot of written very well. So, it is still a classic book. Then another colleague of mine in IIT Madras, T.K. Vardhan, Bhaskar also is there in Department of Aerospace, he is a student. So, now he is a professor. T.K. Vardhan again he retired about more than 10 years ago. They have written a very small 100 pages, 150 pages, it is like a class note, I will not consider it as a real book, but they have written a small analysis of plates, Narosa. Then there is a very good, very authentic book on shells by C.L. Dime. C.L. Dime is a good book writer. He has written many other books also on energy method, finite element and things like that. So, he is a good book writer. So, introduction to theory of, it is very concise, it is there in our library. So, you can see that. Then the next book I will say is P.L. Gould. Of course, there are many other books, Gould, Washington University, Washington in St. Louis. So, he is still there and he worked in this area of shells, and it is for the first time I find that plate is after shells. You see, see normally plate is a simpler object than shell. Shell is much more complex, but the title says, and then I was intrigued by, I took the copy from library. See on the main cover, if you can see here, main cover it is written analysis of plates and shells. So, it is in the proper order, and but then the moment you go inside, analysis of shells and plates, I cannot imagine that they can do this kind of editorial mistake, analysis of shells and plates. Okay, So, this is his book, this is a good book, good companion, but then I will say I will give for shells there is nothing better, to start with, there is nothing better than Krauss. Krauss is a good book, and then J.N. Reddy also has written, I think I have already told you, plates. He has also written a book on shells. I have not. Now he has written a combined book which has come in 2004, which is laminated composite plates and shells. It is a good addition. So, this is a good book. It is also available in the Indian edition. So, it has been reprinted. This book. It is about 600 pages, costs about 500 rupees. So, it is a good book. Now, besides this, I will also be referring to some journals. Of course, the classic journal on mechanics, classic journal is ASME Journal of Applied Mechanics, as far as solid mechanics, even in fluid mechanics. Anything on mechanics, if you can publish in ASME journal, I think it is much better than publishing in, it is top. Your rating, although it is nowadays, do you know, there are some impact factor of a journal. What do you mean impact factor? Means how many people read that journal. It depends upon how many people publish in that journal, how many papers come out from that journal. So, it takes into account that. So, impact factor. So, its impact factor may not be very high, okay, maybe about 2, 1.8 or 2. There are journals nowadays which have come very recently and their impact factor is 4 in mechanics. That is manipulation, not real. So, they want to see, but it is a very well established, very mature journal, and same thing is about next best journal is ASE Journal of Engineering Mechanics. ASE publishes, just like ASME publishes so many journals. So, this engineering mechanics takes or publishes good papers. Then there is another journal, International Journal of Solids and Structures, in short it is called IJSS. For vibration problems, and you have Journal of Sound and Vibration. Okay. So, that also has, and in recent time this one has become very popular, and it has very good coverage, very good papers are published in composite structures. Composite because only the material changes. Okay. In the olden days we were only talking of isotropic material. So, nowadays okay. So, next plates and shells, but before plates and shells you should know something called beams and arches. What is a plate? By basic definition of a plate is, see, no matter how peculiar a body is, every body is a 3-dimensional body, every member, every thing is a 3-dimensional. Now, it so happens that see, 3 dimension means 3 dimensions, you have x, y, z, its volume is measured by the three directions, and any point inside it is having a coordinate of x, y, z, 3 or 1, 2, 3, you know 1, 2, 3 also. Instead of x, y, z, we also called x 1, x 2, x 3, new notation. So, we can call 1, 2, 3, x 1, x 2 or x I going from 1, 2, 3. So, these are all. So, a plate is a body, 3-dimensional body, no doubt, but it has got some characteristics. One of the dimensions is small compared to the other two. So, plate, what is the difference? And second one is in the plan area it is flat. So, plate means this one can be called a plate. This, it has got this, the thickness of this book or depth of this book is much smaller than this width and this length, okay. And it is flat. See, flat in this. So, if you consider x y this, so in x y plane it is flat, in z which is the third dimension it is very small. So, h by a which is smaller than b can be considered small compared to unity. So, plate is that, then I will define geometrically, but then this is what is a plate. Of course, it can be supported and then you have to apply load, because any structure you cannot call any body as a structure unless it resists load. Body has to resist load, because then only it has got purpose. So, it has to be, boundary condition has to be provided and then the load has to be provided, then it will undergo deformation. So, this is plate. So, since one dimension is small, what we do, because we have learnt in the first course 3-dimensional problem, this can be analyzed at 3D problem. Yes, you have done problems, you have solved also. Srinivas has 3-dimensional solution, Pagano 3-dimensional solution. Our method we have given how to solve 3-dimensional problem. If these are simply supported, so numerically integrate in, that is very effective method. Okay, anywhere it will work. So, 3-dimensional as such, that means we do not make any assumptions. The equations of theory of velocity are exact, which describe the behavior of any 3-dimensional body. We do not make any assumption, but then such problems which can be solved are limited. Their geometry has to be simple, the boundary condition has to be simple, loading has to be simple, then only I think we can tackle somehow solution of 3D problem. So, because of the nature of this, thickness is small compared to, we make some assumptions regarding the deformation of the transverse normal. See, normal is what? What is normal? Normal to this x y plane. If I draw normal to x y plane, they are all directed in z direction, and that is normal to x y plane. So, normal, and that also defines my thickness, is it not? Thickness will be defined or not in the third direction. So, that normal, what we will do? We will try to assume some pattern of deformation, that when loads are applied, then let us assume that normal just rotates, remains straight or gets distorted, whatever it is, but we make some assumptions regarding deformation of the transverse normal, and by making that assumption, we are now making assumption in the third direction. We can reduce that dimension, because we are making assumption means you will be assuming some function for the displacement in z direction. So, in the formulation mathematical model, there will be some integration through thickness, and then we can integrate that function completely. So, ultimately you will be analyzing only a two dimensional body, which will be just a sheet of paper. So, this one, a body which has got two dimension and third dimension is negligibly small, is nothing but really two dimension. So, 3D problem is reduced to two dimension. So, plate is an object, a body whose one dimension is very small compared to the other two, it is flat, and its behavior is governed by the behavior of only one plane in the thickness. We will choose one plane, normally it is chosen as the mid surface, mid plane or mid surface as you call it, mid plane. So, we will study the behavior of only one sheet having infinitesimally small thickness. So, it is a truly two dimensional. So, in the process we reduce the three dimensional problem to two dimension. So, that is plate, because I just wanted. So, that is why I have written here two dimension. Shell also, the difference between plate and shell is only one thing, not much. What is the difference? Anybody? What is curved? See, this is having some thickness and this is a plate. A curved plate like this, I give a curvature initially, is called shell. So, basic definition is, if somebody knows about what is a plate, so rest everything, only thing is there is some curvature. It can be curvature in one direction, curvature in two direction, it can be anything. So, a curved plate is a shell. Again, the only difference is here you will have to use curvilinear coordinates to define your point inside the shell. So, shell you needs shell, the equations become much more complex because of curvature. The normal that shell will have, see in a plate, since it was flat, the normal in anywhere original normal, they were all pointing in z direction. In a shell, in a simple shell, this is the simplest shell, it is called what? Cylindrical shell. You have in IIT so many cylindrical shells, have you noticed? They are there at many. Shell has got, and the good thing about behavior, this becomes much more, it can resist much more load than a plate shell, the moment you give a small curvature. So, you can make it much more efficient, thickness can be reduced for the same load, which you same span, everything. Here the normal will be changing its direction. See, if I draw a normal here, it will be like this. If I draw a normal here, it will be like this. So, normal changes from point to point direction, and that complicates the entire mechanics. The whole formulation gets complicated because of this. So, this is what is the plate difference between plate and shell, but shell is very challenging, and one should know the theory, if you want to learn something, because you can create. But before this, so both are two dimension, there also we will reduce the three dimensional problem, because thickness is small, to two dimension. We will study the behavior of only a curved sheet, a curved reference plane. Thickness will be all subsumed into that, thickness will be all compressed, it is called single layer, compressed into that sheet. Once you know the behavior of that sheet, it is possible, because you have made some assumptions regarding the deformation of the normal. So, you can find out displacement at any point in the thickness. That is what is our approach. So, problem gets reduced to again two dimension. So, from 3D, I think where I have written 3D. So, this plates and shells are basically 2-dimensional problems, but then before this, which you have already done beams, you have already done in your undergraduate arches. You should not lose the sight. There the only one coordinate comes in the picture, x coordinate or s coordinate in the case of arches. Because what is the difference between a beam and a plate? Out of the 2 dimensions that we have got in a plate, A and B, B becomes very small compared, B also becomes very small compared to A. So, this dimension also gets reduced, and you have only a planar problem, 2D plane elasticity problem, and that gets reduced to 1 dimension. So, beam will give you 1-dimensional formulation. Similarly, arch will, the difference between beam and arch is it is curved. So, that also will be only in 1 dimension. So, it is a 1-dimensional problem. So, if you want to study shells, you should know about arches. If you want to study plates, you should know about, and that is how the theory also has developed. First beams came in the, first people started the basic assumptions, how to take the deformation of transverse normal in a beam or arch, then that was extended to 2 dimension, even if you see the history of mechanics. Then of course, 3-dimensional panels you already aware of. Basically all problems are 3-dimensional. So, you can have a flat 3-dimensional panel, 3-dimensional, really 3-dimensional, or a curved 3-dimensional panel, which can be solved as it is if you do not want to make assumptions. So, it goes from here upwards, it goes to here, and then from here to, this is 1 dimension, and then you can also go from directly here to here, 2 dimension. So, and we already know that normally this study of 3-dimensional continua, 3-dimensional bodies is a traditional part of our postgraduate masters and PhD program. It is not taught in undergraduate, or even if it is taught, I think sometimes elective in the final year, theory of elasticity, but the students do not understand what is the difference between theory of elasticity and structural analysis, because it is combined. So, this is okay. So, now next one, we already know, I will just quickly go through this. Theory of elasticity is the foundation for all these courses. So, without theory of elasticity you cannot learn either plate theory or a shell theory or a beam theory, or of course, beam theory is learned before because it is taken as a simple element and then it is introduced without reference to as an approximate solution, because all the engineering, all the elements that you come across in practice, they are simple ones. So, we develop some theories, but basically they all are derived from 3 dimension, and we know there are 3 sets of equations which describe the behavior of any 3-dimensional, that is equilibrium, compatibility or strain displacement, and material constitutive law. Now, in the last 20 or 30, now 50 years, because history of composites, see the first paper on composite material, composite means non-isotropic. Up to 1960, the whole world was only dealing with isotropic material. There was no concept of anything other than steel, design, machine parts, and any other material also was always assumed to be isotropic. So, the only thing up to 1960s, no papers, nothing on anything. First paper appeared in 1961 on orthotropic material. Orthotropic, orthotropic, it means properties are not same, properties are different in 3 orthogonal directions. So, orthotropic material, and then it started growing. orthotropic, then number of layers, thickness can consist of number of layers of orthotropic material or isotropic material. So, the total thickness is highly complex material. So, like this, so whatever has happened in the last now 55 years is mostly on materials. We have developed number of new materials, we have the capability to analyze these bodies which are having, but of course, our basic formulation has remained the same. It is still 3D elasticity, it is still two dimensional plate or shell or one dimensional, but thickness in the material in the thickness direction, material is changing its property. Now, recently for the last 10 years we have another new material which is called, first it became layered material like this, one layer like this, next layer like this, third layer like this, fourth layer like this. So, this is called fiber orientation or orthotropic properties are coincident with x and y. But then people said, no, why should it be coincident with, I want to use my material more efficiently. So, then they made it like this 45 degrees from x and y, let my material orthotropicity. Of course, it introduced some complication, but then it was a good way of optimization. So, first phase of about 30 to 35 years was on orthotropic use of orthotropic material in a layer wise manner. So, it is called layered composite material. Suddenly, about 15 years ago, we got an idea from a Japanese inventor that in many applications, one side you have to have heat shield, means temperature is very high, on the other side temperature is normal, room temperature, let us say, or even if you in your spacecraft, when it goes into space, because of friction with the air, outside becomes very heated, inside you can maintain temperature, because it has got some thickness now, all these shells. So, they said, why not have material which varies gradually instead of layer wise. First we tried layer wise. So, what we will do, we will put one layer of, let us say, ceramic. Ceramic is very good in high temperature behavior. Plastic is not, plastic will melt. Steel also has got some highest temperature to which it can go, aluminum also. So, depending upon the use, depending upon high temperature, people varied the layers and then they got, but then they found that after some time there was this, the material which was used for gluing, for joining, that became like this. So, it is called delamination. This one, these two sheets here, because stresses and strains will be there. So, here this will become like this, not everywhere it will be, there will be some. So, it is called delamination. Either one will just split or one will also shear, one layer will shear. So, these are the two modes, one either splitting, it splits, or it just undergoes shear, in shear it will fail. So, then what was the solution? These Japanese, they came with the idea, why not have develop a material in the factory which is, whose properties are changing continuously through thickness, and they gave the name of this material as FGM. Anybody has heard about FGM? FGM, what is FGM? Functionally graded material. Functionally graded, depending upon the function, I will grade my material uniformly by a continuous function, not discretely. Earlier it was discretely, every layer had discrete properties. So, since there was a discrete properties, the every layer interface was a layer of singularity. There was singularity existing, two layers of different material. So, it will use to split or shear. Now, they want continuously distributed, manufacture a material which is continuously distributed property. So, it follows some function, and if you define that function, it can be manufactured. and then it can be used in various applications. So, it has now been being used in thermal as a thermal shield in aerospace and also in atomic energy for the reactor, inside the reactor, because inside is very hot, outside will be room temperature. So, they want to use this functionally graded material for their main reactor. So, this is still in infancy in its it is not that 100% technology has been, but these are okay. So, this is 3 dimension, but idea is there is always a beauty in obtaining why. So, 3 dimensional, please revise your all the basic equations that govern the behavior mathematical model for a 3 equilibrium, strain displacement, constitutive relation. You please revise, and then the Hooke's law, material constitutive relation, for example, simple isotropic material I have written here, you can write it for any other material. Material properties are point properties, not a layer or a entire thickness, it is point, it defined at a point P. So, you please, and then the mathematical model is always made out of governing equations, and then you have to have the loading and the boundary condition, and then it defines also what we call mathematically a BVP, boundary value problem, or if it is a dynamic situation, then it also we call it initial value problem, initial boundary value problem, because boundary value anyway is there in space, but one more dimension comes, that is time. All your quantities vary with time, becomes in a dynamic problem what happens, every particle has having its own displacement or its stresses or anything velocity as a function of time. So, one extra dimension x, y, z and comma t, it becomes a 4th dimension. So, in a plate what it will become? It will become x, y and t, z anyway will be subsumed. In a shell what will happen? It will be in a shell, because it is a curvilinear coordinate. So, we will call the coordinates as alpha, alpha and beta, or alpha 1 and alpha 2, and then t. So, it becomes 3 dimension in real sense, but of course, we do not solve problems by addition of time as one extra dimension. 3 dimension you can visualize, 4 dimension can you draw an element 4 dimension, people talk of n dimension also, n dimensional problems. So, there is a way of what is the way of handling time? We what to do? No, but then what is the process? Because you are having x, y, z and t, space and time, any quantity, any function phi is a function of space and time. What you do? Separation of variable, basic, the concept is we separate space and time, and any function which is a combined function or a coupled function of space and time can be written as a product of space function and multiplied by a function in time. Of course, not only one product, but there has to be number of such product, it is a series, it is a you have to have, then only you will get convergence. So, by separation of variables we get, and in the process what we do, if you solve your if you discretize your boundary value problem, then you will get ordinary differential equation in time for every point. So, that is the way we solve our. So, anyway, boundary conditions are extremely important, initial conditions are extremely important, boundary conditions, initial conditions. Then so, I think by now you must have understood the importance of or the role that 3D elasticity plays in our problems of mechanics, and so our challenge has always been, because 3 dimensional problems leads to partial differential equations in 3 as 3 independent coordinates. So, it is very difficult to solve, almost impossible to solve. So, how to? So, shell and plate gives you a way, okay, you can reduce one dimension. So, 3 can be reduced to 2 and 2 can be reduced to 1 in beams and plates. Beams and plates becomes very easy, but plate and shells also is in between, is neither difficult nor very easy. So, that is what. So, now based upon geometry, we have I think this is based upon geometrical dimensions. There is one way of classifying beams, plates and shells or arches. I think I should add all the 4: beam, arches, plates and shells. One based upon geometry. How do you classify? So, one is called thick beams, arches, plates and shells, thick. Other one extreme you take thin. That is why in the title of the book you see some books are having thin. The meaning of thin is thickness divided by the one of the dimensions, which is small. If you take the ratio, then it can be considered small compared to unity. It is a small parameter. Is it okay? H by L. For example, in a beam what we do, thin, what is a thin beam? When we can have this, that thickness divided by length of the beam can be taken as small, because we will make some assumptions somewhere because of this, if it is thin. So, then we call it thin. If it is not, similarly in the plate, supposing you have A and B and thickness, one dimension is A and let us say A is less than B. So, you take the ratio H by A. Why I am taking H by A? Because anyway B is bigger na. So, ratio you want to have better is less than unity. So, H by A less than unity, then we will call it thin. Otherwise, it is moderately thick or thick, whatever you want to call it, there are so many definitions. So, geometrically a beam we call it thin if the L by H is something like 15 and above, then we can consider them to be thin. Geometrical, there is no, I am not telling you interior what happens in the interior of the body. Geometrically, if the length to thickness of a beam is more than 15, then we call it thin. 15 to 25 we can call it moderately thin. Span by I am just reversing L by H, span by thickness. So, 15 to 25 we can say, and more than 25 or in fact more than 50 it becomes really thin, 100, 200, you have also beams where you have, and same thing is true for plates and shells. That is, plate, if it is a thin, if A by H is more than 20. It is a very geometrical, very approximate definition, there is no basis, but basis I will tell you a little later what is the basis, because it has to do something with the mechanics. So, this is the geometrical definition, okay. And similarly for shells. Shells, in the case of shells what we do, see, because this is curved, shells the other dimension we always take the radius of curvature, not A by B, we take H by R, minimum radius of curvature at a point. There can be two curvatures. So, minimum one H by R minimum, I think somewhere it should be there. Yes, H by R minimum, that defines thinness. So, if it is, and we can say mathematically that H by R minimum can be considered to be less than unity, say about again about 1 by 20, 1 by 20, 20 is okay, 20 definitely up to 20 you can take, 1 by 20, then it is thin, otherwise it is either moderately thin, moderate, not very thin, and then after it goes beyond, then it becomes thick. Thick means you have to use 3 dimensional theory. In between we can have some better assumptions on the deformation of the normal. In the very thin we can have the simplistic assumption regarding the deformation of the normal. So, this is the only difference between thin, moderately thin and thick. Thin means we will assume that transverse normal deforms in a very simplistic manner. We always make assumptions regarding the transverse normal. So, now in the case of plates and shells, there are 3 things that are extremely important. One is the thickness, because thickness governs everything, everything that follows thickness, h by r, h by a, thickness is very important of any element. Then the edges, because that defines the your size. Then what else? What else? There is one more thing. Not loading, no. Nothing else? No, no, not loading. Loading is, anyway you can put any load. So, thickness is extremely important, then the edges, boundaries, and that is a boundary condition. And the most important is the mid surface, because ultimately your 3 dimensional problem is going to be reduced to 2 dimension, and we are compressing the 3rd dimension and making it a small sheet. It is like your what you call in mechanical engineering, you compress and get a very thin sheet by, there is a process, it is called anything. If you want to put it under press, heavy press. So, what it becomes? It is called, there is a particular name. So, there, so 3rd thing is thickness, mid surface and the edges. These are the 3 important things which will define the entire theory of your plate, because we will be studying the mid surface. Okay. Now, how do you come to mid surface? Because something has to be done. So, we will take this up. I hope I have given you good background. So, we will take it up after 5 minutes.